Thank you guys all for coming here. Bright and early, first talk of the day, track 3, rocking it. This is our first speaker, Jonathan. He is going to be presenting an introduction to the Witchcraft compiler collection. I hope you guys really enjoy it, and I'll let him take it away.
Thank you, brother. Good morning, DEFCON. It's a tremendous pleasure to be here with you. We're going to talk about some badass reverse engineering, hopefully. As you saw, we got some technical problems, but hopefully, with a bit of imagination, we managed to see everything. So my name is Jonathan Brossard. I have a whole lot of content to share with you today. So I'm going to start with the boring things a little bit, and hopefully we'll switch very quickly to full demo stuff. I cannot give the full feedback, the full prerequisites and go through why everything works. So I'm going to stick to the demos and try to outline why the things which are a little bit touchy work. But I can assume that you already know about the ELF format, you're familiar with POSIX, and basically the more reverse engineering you've done previously, the more I think you'll be able to appreciate this talk. Okay, let's get started. So thank you very much for coming this morning. I know it's 10 a.m. DEFCON is starting, so you should all be exhausted by now. The real motivation of this talk is to share with you a new toolkit to do reverse engineering, which really facilitates a whole bunch of things that I thought were impossible before even trying to do it. So it's published under MIT license. I'm in a dual MIT and BSD license because I'm reusing components which were already licensed this way. And I would very much like if you contributed to this Witchcraft compiler collection. You don't have to be very familiar with C or assembly to do this. As a matter of fact, you can write all the code you need on top of this framework using Lua, or a weird programming language that stems from Lua and that we created specially for this tool, which I call Punk C. Okay, so quickly, who am I? So to introduce me, I thought it would be good to tell you about my love relationship with DEFCON. My first talk ever was at DEFCON 8 years ago. It was on BIOS vulnerabilities. Basically, we found a new class of vulnerabilities on the BIOS, which allowed us to pop using a single exploit, TrueCrypt, BitLocker, McAfee endpoint, and a fair bit of BIOS firmwares. Then I've been rejected pretty consistently at DEFCON until 4 years ago, where I gave this talk on hardware backdooring. This is a talk I really liked because I did it with the people who engineered an open source BIOS called Coreboot. And the real pretext of this talk was to work with them. We did this for our conference in Paris called No Such Conference. And basically, they dropped the project and I pursued it a bit. And yeah, it ended up pretty cool. The MIT technology review gave me, gave a review on it and said that's a computer infection that can never be cured, even if you reflash the hard drive, even if you change the hard drive or erase your BIOS and things like this. Incidentally, that's where my ex-teachers in engineering school stopped talking to me. The thing also got featured in, more mainstream press. It got featured in Forbes, which is interesting. They had pretty much the same feedback. I'd like you to pause for a second and imagine, the kind of online presence this gives me. Imagine, I get to meet a girl on Tinder or whatever, and she Googles me. She's like, "Oh, awesome, he's been on Forbes." Yeah, for writing malware, baby. So I'm telling you, I've been pretty consistently rejected. That's a message to you if you submit to conferences. Being rejected is part of it. It's normal. It's completely expected. So stuff that didn't make it to DEFCON, but that I presented at Black Hat, that was a pretty cool debugger, I thought. It's called PMCMA. You can find the code base online if you're interested. Basically, the normal way it works is you have one debugger who's debugging a debuggee, and you get a one shot. If you crash the debuggy, like you have to restart everything again. So instead of doing this, my debugger was attaching to the debuggy, forcing it to fork to replicate itself in memory, and then we'd work on one fork at a time. That's the routine you can see over there. Finally, last year, we did a presentation with my team from Salesforce. We pretty much resurrected SMB relays, and our contribution was to show that it doesn't work just on LANs, it actually works from the internet. I saw on the schedule this year that there were more talks on SMB at Black Hat, so yeah, I hope we resurrected something. If you run Windows networks, you want to watch this talk, because this is still unpatched, and this is affecting every version of Windows. Okay, this slide is brought to you by the Security Vacation Club. What do you do once you've done all the work to create a badass presentation and that you have massive content you'd like to share? Well, do it more than once. There's all this list of very cool conferences. So Aki2 Argosom in Paris. I'm a bit biased because I created it. Aki in the Box in Malaysia, which is really awesome. H2HC in Brazil, it's insanely good. SciScan in Asia, things like ShakaCon in Hawaii. I'm also part of the program committee of that one. Infiltrate in Miami, Recon in Canada, Only Reverse Engineering, very, very cool. KiwiCon in New Zealand, Eco Party in Buenos Aires, Zero Nights in Russia. So basically, if you do all the work to create one presentation, I suggest you, enjoy your Security Vacation Club tour and give it to all those conferences. There's one left I didn't put in the slides because it's a trap. It's called RoxCon in Australia. I was supposed to go there for 1 week to speak, and I stayed 4 years. So it's a trap. Okay, a bit of disclaimer, and then let's go to the meat. So my employer does not wish to be named, even though I just did. They're not associated with this talk, and this is my personal research. On the upside, it means I'm free to share it with you. There's no intellectual property problem. But on the downside, it means you want to do reverse engineering, and you're on your own. What do you do in this case? You call EFF to the rescue. And before anything, I'm going to ask you to give a big warm, a big clap to the people of the EFF, because they've been amazing. Thank you very much. I know some of them are talking today, so they're definitely around. If you manage to catch them, pay them a beer, because they're really helping us when we're in situations like this where we cannot afford, legal advising. And if you do reverse engineering, they have a nice FAQ that I suggest you check. The URL is on the slides. Okay, so my employer doesn't want to be named, but he's recruiting. It's a badass security team. If you saw the attacks on Breach and things like this, denonymizing SSL, Ravage, which was a very cool tool to profile Java, or the research we presented last year at Black Hat, yeah, feel free to decrypt those slides. I think we're cool. The legal department and the PR department are very unlikely to decipher this slide. In terms of agenda, I'm going to talk to you quickly about why I started this project and why, it's relevant, hopefully. And then we're going to do some really serious black magic with the Witchcraft compiler collection. I show you, what are the main tools in it. I show you how to transform the shared library, I'm going to show you how to transform an executable into a shared library. Okay, that's not supposed to fly, but that's super helpful when you do reverse engineering or exploit writing. Then we go further and we'll completely unlink an ELF to a relocatable file. And then we'll extend that and go a bit crazy. Okay. I don't get to see my slides, so it's a bit touchy for me too. Quickly, let's imagine we're working on an application and we don't necessarily have the source code. Honestly, even if you have it, it takes time, to recompile things, possibly to adjust your tool chain. You have missing dependencies and things like that. You often don't have the right headers and things. So working with source code isn't easy. I'd really like to work with binaries directly. As an example, I took a very old version of SMB. It's called SMB Server 1532. It's basically a predecessor of Samba. So if you do static analysis, that's a pet project I run on the side with another company I work with full-time. So I have two full-time jobs, right? The one with the company who doesn't want to be named, one with a startup in France, and I have so much free time that, you know, it allows me to do more research and share it with you. So basically, that's a thing we run with our startup in France. You can register for free. It's only for security researchers for the time being. It does full-featured static analysis, so you upload your binary, and you get back a bunch of metrics. On this slide, like the more red you get, the better it is. You can see that it's checking, you know, 5 different aggregated metrics. Without going into the details, the bit we're gonna care about today is like, okay, you can see that the binary, for instance, is compiled without ASLR, without Fortify hardening, and things like this. But what we're really gonna look at is like finding proper vulnerabilities from this binary without using source code. One which looks pretty cool is the one with fopen right here, which is opening, I mean, it seems like it's opening a file with a predictable name in write mode in /tmp. Since this thing is running as root, there might be, you know, possibility for a symlink attack and basically a local privilege escalation. The thing which is interesting here is that we don't have a full backtrace. So the way the tool works internally is like, it does like, you know, decompilation, I mean, disassembly, decompilation, full static analysis on the binary by using symbolic execution. We wrote the engine ourselves, so it does it straight on binary. And a problem you commonly face when you use advanced techniques like this is that you don't have a full stack trace. So I have only a partial stack trace here, and I'd like to verify this vulnerability does exist. Okay, another way to do this is to hit this problem is when you do fuzzing. Like often, like in this case, this is taken from the Bugzilla of Red Hat. It's also SMB, which seems to be crashing. And we have only a partial stack trace. And this thing is actually bizarre, right? Because it's not called from main. So we don't really know what's happening. What I know is that I don't want to call the whole thing from remote by sending packets. I'd like to verify if the vulnerability exists by calling directly an arbitrary function inside the binary or inside a shared library. So that's our problem statement today. I want to be able to call any function inside any binary without having to craft an input to reach it, and without necessarily going through main and whatever layer of function and then reach it. I want to be able to call those functions directly. Okay, so here are the components of the Witchcraft compiler. It has a linker, which is a badass tool which patches 1 byte in binaries, but its power is incredible. You're going to see this. We got the WCC, which is the core compiler, which is the tool which takes a binary as an input and gives you relocatable files that you can later on relink to generate new shared libraries or relink against your own code and like get new executables. And finally, we have the Witchcraft shell, which is by far the most complex. It's a full dynamic interpreter and scripting engine built on top of Lua. And yeah, we're going to see that this is pretty cool. With this shell, you can write your own scripts. So an example of scripts we're going to see today are WCCH and WLDD. Let's go to the meat, libification. So if you did one class of computer science and C programming, the first thing people tell you is that what we're going to do today is impossible. Let's start with the demo. I don't see anything. Oh, fuck. Yeah, I know you're not seeing this. Okay. Here we go. Okay, so for instance, to give you an idea of where is the state of the art of decompilation and why we're not going to take this route. So this is a elo.c file, okay? And I'm going to show you the equivalent code generated by possibly the best decompiler you can get for free. It's called Snowman. It works in two modes, either on top of IDAR, or it has a mode where it can run by itself autonomously, which is free. So to give you an idea, like when you decompile these two lines of code program with Snowman, you get something like this. Okay, so that's the source code which is supposedly equivalent. So if you take that path to decompile a real binary, let's take ProFTPD for instance. It's 200,000 lines of code. Okay, you're going to get about 200,000 times this. So decompiling this and recompiling this is not reasonable. If we give it a try, just for fun, let's try to recompile the one from Snowman. I'm just going to grab the errors. Maybe. I don't see shit. Okay, let's drop this. I think you got the idea. Okay, so what's libification? Basically, we're going to take an ELF file. This is the main header, the ELF header. We're going to patch 1 byte. We're going to tell it, you're not a binary, you're not an executable binary anymore. You're a shared library. So patch it from etexec to etdin. So let's do it with ProFTPD, for instance. Let me get this full size. Can you guys see any of this? That flies? Yeah? Okay, so as an example, let's take ProFTPD. And let's assume we don't have the source code. Let's copy it to /tmp. If we check the type of the file, okay, it's obviously an ELF executable, as seen right here. I'm going to use WLD, so the first tool from the Witchcraft compiler collection. It takes only one option, which is libify, and then the name of the binary. So I'm going to run this, and let's now check the type of this file. Okay, and surprisingly, it's a shared object. Okay. But what's crazy now is that it really is a non-relocatable shared library that I can relink against my own applications. So let's check how to do this. Okay, so that's a sample program which is going to load /tmp proftpd.so into memory. So let's start with renaming ProFTPD we just patched into proftpd.so. It's going to DL open it, so load it in memory, which returns a handle which allows you to call dmsim and find the address in memory of any of the symbols in there. What I'd really like to call is this function called pr_version_get_string, which returns inside ProFTPD the version of ProFTPD. So what's very crazy, let me show you the makefile quickly. There's nothing very crazy. Okay, we're just using a linker script to avoid GCC giving by default the same address to this program and to proftpd.so, so they do not collide in memory. So what I do is basically my demo is mapped much higher in memory to make space for this non-relocatable shared library. And what's very crazy is that this thing actually works. Okay? So if you look up there, it really returned like 1.3.3d, which incidentally is the version from ProFTPD, which we got from the shared library. Isn't this insane? Okay. So that's exactly what we just did. You can see that we really just patched one byte in memory. So without going into, the crazy details, there's a couple reasons why this works. The first reason is that, and I need to show you something else, which is very crazy, is that the library we just patched is still a valid executable. That is completely unexpected, right? So the reason this works the reason it's still a valid executable is that basically the way we pushed full ASLR in the Linux kernel is by allowing you to compile your binaries as a shared library and execute them at any address in memory. So yeah, you can have a binary with technically a shared library. We're going to see that a bit more on this later. The other thing which is a bit crazy is that this newly recrafted like shared library cannot be remapped in memory, right? Because it was never meant to be relocated that way. So we have a shared library, but that can only be mapped at a single address in memory. This actually does exist in the normal world. It's called prelinking. It's the fact of giving a base address to speed up booting, essentially, to shared libraries. And yeah, so that's exactly what's happening in here. Okay, let's do a demo with Apache. I'm going to show you that you can actually relink against Apache, which is not a shared library, but pretend it's a shared library. Okay, so let's look quickly at the source code. Okay, so it does nothing crazy. It tries to call ap-get-server-banner, which is a function which is defined inside Apache. And to do this, we're going to link straight away against Apache as if it was a shared library. So let's type make quickly. Okay, it's complaining. Boom. And if now I run this application, it's very crazy, but that also works. So Apache is not really a shared library, right? It's an executable, but it's compiled as etdin to have like full ASLR. And if you link directly against it, you can actually call functions directly inside it. This is so amazing that I'm tempted to end my talk here. Okay, if you look at like the way, you know, if you try to print like which shared libraries this application is linked with, you see that the first one is very much Apache, and that looks very crazy, but it works. Okay, let's go one step further. So this technique we just used is by far my favorite because it's cross-platform, it works across architecture, and it's super stable. There's no such thing as like complicated analysis that might fail and stuff like that. Like all we did was patching 1 byte, which, you know, incidentally is pretty reliable. If you wanted to go one step further, and instead of transforming an executable into a shared library, go back to the output of a compiler before the application is linked. So we'll call this unlinking. Well, we're going to use this tool called WCC, which is a lot more complex and less portable. And you know, basically, what it tries to do is recreate the relocations that were missing from the final executable, and add them to the binary so that you can relink it. So the normal way to do reverse engineering and to solve this problem would have been this: when you have compiled source code, you would use a decompiler, which is totally not what we're going to do. We're just going to go back to the relocatable files, and once I have the relocatable files, I'll be able to relink them again. So the command line is made so that there is zero learning curve. If you know to use GCC, it takes essentially the same parameters as GCC, only it doesn't take source code as an input, it takes a binary. Okay, I'm going to give you a demo on this. Okay. So I have a small file here, which is a small C file, and it has a whole bunch of relocations. Okay, it has a number of imports. It has strings which are in the read-only data section. It has strings which are, you know, passed as arguments. So yeah, it has pretty much all the type of relocation that do exist. I'll share the source code so you guys can verify this. But essentially, what we're going to do is first compile it. Then, so the normal compilation will give us a binary called small. Then we'll use the Witchcraft compiler to go back to a relocatable file from this final binary, and we relink it as another binary using GCC called small2. And the question is like, does small2 actually runs? Because that would be very crazy. So let's compile it quickly. So if I run small, which is the original binary, it tells me something like hello from DEFCON. You can see that WCC, so let's redo this manually actually. Let me redelete this and this. Okay, so I have only this small binary. I'm going to use WCC, the tool I just told you about. If I played stupid and I assume I want, if I wanted to use GCC, so I would like to do something like this essentially, and tell it give me, small WCC.o, and I'd like it to be a relocatable file. If you run this, like GCC is going to be like, I don't understand what you're trying to do. The input is not a source, source code. But if you do it with WCC, it's going to be like, yeah, okay, let's do this. And it gives you this relocatable file that then you can absolutely relink into small2. And what's amazing is that small2 does the same thing as the original binary. This sounds very crazy, doesn't it? So if you like it, I'd really like you to contribute back to this tool and extend it. For the time being, it works mostly on AMD 64. I'm trying to port it on ARM. And the drawback, as opposed to the first tool, which worked everywhere because we were just patching one binary, here it's a bit of work because we have to deal with all the type of relocations for all the type of CPUs. So I need your help with this. Okay, I'd like to explain you one thing. I choose, so to architecture this, the front end is basically libbfd, so it's like objdump and tools like this, or objcopy, which has a nice, the drawback is that it's not very precise, but the advantage is that it works with many type of binaries, not just ELF files. So technically at this stage, we can try to do very crazy things like, let's do Witchcraft, baby. Let's try to transform a PE file into an ELF file. I'm running late, so I'll let you play with this at home, but that basically works. We have one problem here. It's like, I don't know what to relink this with, right? So an idea would be to use like the libraries shipped with Wine, which already give us, the Windows API compiled as an ELF file. This is left as an exercise to the reader. We're going to do something way more crazy right now. Can you run OpenBSD binaries natively on Linux? If you've been to, if you've done a bit of engineering, like that's not supposed to be possible. Like technically, you're supposed to have a virtual machine. Let's do it without a virtual machine. Proper Witchcraft. Okay, so we could do this manually. I'm going to do it with a makefile. So the original binary, yeah. So here the original binary we're going to play with. You can see that it's very much an OpenBSD binary. Okay. The source code is trivial. It's basically this. So it's doing a bunch of printf in a row. Okay. Here comes the main file. Fuck the display today. Okay. So we're going to copy the binary, blah, blah, blah. Okay, basically, there's a couple problems. The dynamic linker is expecting to find does not exist. So to show you manually, if I do like a strace on this particular binary, that was not supposed to work, actually, because I already patched it. Okay. Fuck. Okay, let's just run it. I'll explain you how it works later. So basically, the dynamic linker is not the right one. This is hard-coded inside the binary, inside the interpreter section. I could patch the binary to put my own dynamic linker. Instead, what I'm going to do is copy my real dynamic linker to the location is expecting the dynamic linker to be encountered. Okay. Right. So then it has a little bit of a problem. It's looking for libc, which is called libc.so.62.something. And my libc is not called like this. So I could patch the binary there again to tell him, like, no, look at like the libc I've got. But instead of this, I could also copy the my own libc to the libc is expecting. And if you do all that, I share all the material so you can reproduce yourself. But essentially, amazing. Okay, if you, there's a last problem, it's like it has a missing dependency on, right, if I try to run it now, it has a missing dependency on @exit. So what we're going to do is use LD preload to give him you know, a shared library with all the dependencies is missing, like @exit. We don't really care, right? @exit is a function which is called, basically, when you exit, to called, you know, deconstructors and things like this. So I don't really care. Long story short, if you look at the last line, you do the LD preload, you run this OpenBSD binary, which has been slightly adapted inside a Linux machine, and it does print what it was supposed to print, which is also very crazy because there's no virtual machine, and this was never supposed to work. Okay, now let's go to proper witchcraft, and I'm going to introduce you to a programming language that comes from basically implementing a sort of reflection in C inside a Lua interpreter. So what I'd like to do is basically to get reflection-like features, but on binaries. Reflection is typically something which only exists on a virtual machine, right? It allows you to load classes or binaries in memory and instrument them, like get a bunch of information on them, like what are, you know, what type of argument they're expecting and things like this, and then to invoke them directly in memory. So I'd like to do that, but without a virtual machine, straight from binary. So it's based on dlopen, which is the function we used earlier to link with ProFTPD. You can compile it with luajit, which gives you just-in-time compilation in memory. There's no ptrace, and it typically doesn't work like any you know, debugger you might have used before. I don't see the slides, so I'm gonna go quickly on this, and we're gonna stick to the demos. 10 minutes? Okay, so it's time to activate. Okay, since I don't see the slides, I'm just gonna run it for you. Okay. Okay, that's the SMB server I showed you earlier with the static analysis thing. So let's copy the SMB. It's already there. Fuck that shit. Okay, nothing works. So I'm gonna load like the ProFTPD binary we've patched before, and I'm gonna you know, showcase you the capabilities of WSH. So we just loaded it in memory. It has a bunch of built-in functions. When you don't know one of the functions, you can use you know, the help, which is the only documentation you'll get in this respect. Okay, so let's call this function, for instance.
Hey, everybody. Is Jonathan doing a good job?
Thank you, folks. Okay, I really want to show you this because it's beautiful. So we can do crazy things like print the section headers, that the output you would get from NM typically, only this is dynamic and this is recursive over all the shared libraries inside your memory. This is a feature I always wanted because it's not built in GDB and it's always a problem when you're trying to do this. You can have the program headers. You can look at like what are all the functions which are loaded right now in memory. Let me show you this first. You can ask him to print what are all the libraries that you have loaded in memory. I just loaded pre-FTP, but that also loaded all its dependencies. So if we look at like all the functions that this has actually loaded in memory, there's a fair bit of them in a bunch of libraries, and we can now invoke them straight away. So already we got like 6,000 functions to play with in memory. I don't even know the prototype. I know nothing about them. So let's look, for instance, if there is a function which print the version or something like this inside proftpd. Okay, so like before, we find this version called PR_version _get_number. I'm going to print this inside a variable, and if I print the variable like before, that's not what I expected, because that's not the right one. Let's try with the string one. Yeah, so like before, that's printing me internally the version number. No. You've seen nothing. The real good thing is, so the real bad thing, and why I took Lua, I'm going to try to activate, is that you can have more than one return value. So I'm gonna tell him, okay, I want A, the result of this function, but also give me a context. And now, if I looked at the context, it tells me a whole bunch of things is down, of the context of this execution. So that there's error number, was 0, there's no seg fault and stuff like that. I had not planned to do this, but let's do something crazy. This allows you basically to build static analysis on top of WSH very simply. I won't have the time to explain everything today. Let's just say we want to test all the functions inside proftpd. I'd like you to fuzz them and call them 100 times each. So it's going to list all the functions in memory, and what it's doing right now is like calling them. Okay. Okay, let's stop this for a sec. Dear God, I've been too ambitious. Okay. 100 times is too much. Let's run it like once. And what happens is that it's recording all this stuff in memory, and you can see them right after. Okay, I don't have the time to see you all this. I don't want to sabotage this talk, but that's too bad. We're lacking time. Invite me to your local conference. Yeah, I won't talk about this. I won't talk about this. Future work. What I'd like you to help me with. Yeah, I know, we were super late. So I think this is a very cool base to do reverse engineering. There's a whole bunch of stuff I don't have the time to do. So if you would like to participate, get in touch. Do you have any questions, or do you want me to stick to demos? Oh, there is one thing I need to show you, because it's amazing. What if I wanted to analyze an ARM binary on my Linux machine? So typically, to do this, there again, you would need like a full hypervisor and things like this. What I did is just cross-compile my WSH shell to WSH ARM. Okay. I've registered QEMU in a weird mode to do me, when I execute natively, an ARM binary on my machine. In-memory binary translation. So this is really an ARM binary I'm running on my own machine right now. And what we're going to do with this is load this libslinux thing which comes from ARM. So it's complaining because some dependencies are missing. Typically, you would do this inside a CH root to have all the dependencies. But you can see that, like before, we have a bunch of functions and we can call them directly. Now, let me show you something which is really insane. For instance, okay, let's print, let me get my PID. So that's my PID, and it didn't work. That's amazing. Okay, let's get it another way. I cannot get a shell. That's beautiful. Fuck. Okay, I can have it another way. Let's just look at like the libraries mapped inside memory. So my process is really an ARM process. It's loading an ARM binary, and it's running natively on Linux. The binary translation is also inside the same process, thanks to QEMU and the weird mode it's using. And all of this is just one program in memory. You don't need a virtual machine. You don't need all that garbage. And that facilitates a lot, like, you know, the fact of sharing this tool or having like an ARM binary and calling functions inside it from other application without any reverse engineering. Last but not least, I'm almost done. I told you SMB server, I wanted to write an exploit for it, so let's do that quickly. We saw before that we wanted basically to call this particular function called reply clause inside SMB server. Do we have the binary here? Okay. So let's do WSH of SMB server. If I want to call reply clause directly, I can. This sex false, by the way, this is amazing. We get to know that it writes, but we didn't decompile. We didn't ptrace. We get that basically by writing a custom signal handler and parsing better, like, you know, the output we can get out of it. Let's give it a couple arguments, and let's see why it's crashing. Okay. So right here it's crashing because basically the second argument, as you can see, is trying to write. So let's map something here. Okay, in Lua, strings are supposed to be immutable, but in PunkC, which is, you know, what's happening in this script, you can break all the Lua rules. In particular, yeah, you can absolutely write to strings. So I'm going to try to this string. It did reply clause, okay. And if you remember, like the static analysis we saw, this is supposedly creating a file in /tmp with a predictable name, which is g something. And you can see here that, yeah, this file was actually created. And what's amazing here is that we can verify results of static analysis without any reverse engineering, basically. And we can call any function we like in the stack trace, even if we don't have the full stack trace, and even if we don't know an input to take us there. With this, my friends, I think I'm done. Thank you very much for your attention today.